to discuss a very important topic for the mathematics student, that is geodesic on a surface. So let us look what is the definition, basic definition of geodesic. Then we will go in detail how we can interpret here at the PG level the same thing under the differential geometry. The geodesics are minimal arcs between 2 points on a surface. It is already at undergraduate and postgraduate level. This definition is already known in different part of mathematics. The main process is solving the Euler-Lagrange partial differential equation for the function that minimizes the arc length between 2 points on the surface. The integral is the parametric equation of the geodesic. So it is in the name of the great mathematician Geodesic, and the arcual length. Geodesic means arcual length, minimum length. Already it is already here the example, a minimal length, and how you can join the points. So it is already here. It is shown in the picture. Now let us look at how we can interpret on the surface under this differential geometry. So let us consider A and B be two given points on a surface. Yes, and let these points be joined by the curves laying on surface. Then any curve having a stationary length for a small variation over S is called a geodesic. Okay, so this is a definition under the differential geometry related with the geodesic. Now, in the mathematical notation and how in the form of the integral, how we can define this arcual length and the geodesic. So let capital A and B be 2 points on a surface R. On the surface, let us consider all the arcs joining A and B given parametrically as U is function of t and V is function of t, where U and V are of class 2. For every arc alpha, let us assume that t is 0 at A and t is equal to 1 at B, so that the arcs are defined in the interval 0 to 1. Let alpha be any such arc length R and S alpha be the length of the arc alpha joining A and B on the surface. Then we know that we have already seen this ds square is equal to this metric, relevant metric ds square is equal to e du square plus twice f du dv plus g dv square, which gives s dot square is equal to e u dot square plus twice f u dot v dot plus g v dot square, so that we can take s alpha is equal to 0 to 1 s dot dt, which is equal to 0 to 1 under root e u dot square plus twice f u dot v dot plus g v dot square dt. Keeping the end points A and B fixed, let us deform the arc alpha slightly and obtain alpha dash. So this is about the mathematical definition how to calculate the arcual length of the curve. Now, our next definition in this connection is if alpha is such that the variation in S alpha is at most of order epsilon square for all smaller variations in alpha for different lambda t and mu t, then S alpha is said to be stationary and alpha is a geodesic. Okay. So here it is also important that the geodesics on a surface are intrinsic in the sense that it is defined by the metric on the surface independent of any particular parametric representation of the surface. So we have to remember that this geodesic on a surface are intrinsic. Now, let us look at theorem. That theorem is very important, and this is known as the first theorem of Geodesic. A necessary and sufficient condition for a curve u and v, u is equal to ut, v is equal to vt on a surface, r is equal to ruv to be a Geodesic is that capital U del t by del v dot minus capital V del t by del u dot is 0, where u is this expression, means partial derivative del over del t by del u dot minus del t by del u is equal to the same may be written as 1 by 2t d capital T by d small t dot del capital T by del u dot, where V stand for this V is equal to del over del t del capital T by del V dot minus del T by del capital T by del V is equal to 1 by 2 capital T d capital T by dt dot del capital T by del V dot. This is equation number 2. Let us suppose in the theorem statement itself, this is equation number 1 and this is equation number 2. Now equation 2 are called GEODESIC equation. This equation is called GEODESIC equation, and we use the usual method of calculus of variation to derive the equation 2. With the help of equation 2, we obtain 1 and then prove that the converse of 1 is also true. So this is the methodology which we will adopt to prove this theorem, but the proof of this theorem is always little lengthy. To prove 2, we need the following lemma. So this lemma is, if gt is a continuous function in between 0 and 1, and if 0 to 1 vt gt dt is equal to 0 for all admissible function vt as defined above, then gt will also be 0. This is the lemma. So on the well established lemma, how we can start the proof? To prove 2, we proceed as follows. Let f u v comma u dot v dot is equal to under root 2t, where 2t u v u dot v dot is equal to h dot square is equal to e u dot square plus twice f u dot v dot plus g v dot square. In term of f, the arcual length s alpha may be defined in this expression. After a slight deformation, the arc length s alpha dash may be defined as, this is equal to 0 to 1 f of u plus epsilon lambda v plus epsilon mu and comma u dot plus epsilon lambda dot and v dot plus epsilon mu dot dt. Hence the variation in S alpha you can, variation means S alpha dash minus S alpha, and this may be defined like this, the difference of the above two equations. Using Taylor's theorem for several variables, we will get on simplification this expression. F of u v u dot v dot plus epsilon lambda del f by del u plus epsilon mu del f by del v plus epsilon lambda dot del f by del u dot plus epsilon mu dot del f by del v dot plus higher order of epsilon square. Now using 6 and 5, we will get their difference, means S alpha dash minus S alpha in the form of this term. We shall simplify the integral on the right hand side of equation 7 as follows. Using the integration by parts, we will get on simplification this equation is 0 to 1 lambda del f by del u dot dt is equal to 0 to 1 del f by del u dot d lambda, and this is equal to lambda del f by del u dot 0 to 1 minus 0 to 1 under the integral lambda d by dt del f by del u dot dt. Since lambda is 0 at t is equal to 0 and t is equal to 1, we have this term is 0. Hence 0 to 1 lambda dot del f by del u dot dt is expressed into the term minus 0 to 1 lambda d by dt del f by del u dot dt. And this integral will are equivalent to this integral, equation number 9. And now on simplification, we will get S alpha dash minus S alpha is equal to epsilon times 0 to 1 lambda L plus mu m dt plus higher order of epsilon square, where L is this L may be expressed like this and M may be expressed like this. For the arc alpha to be geodesic on S, S alpha should be stationary. It is stationary if and only if the variation is at most of order epsilon square. For all smaller variations, since epsilon is greater than 0 and this term is of the order epsilon square, then equation T implies that this 0 to 1 lambda L plus mu m dt is 0. For all admissible function lambda mu of the class 2 in between 0 and 1, such that lambda is equal to mu is equal to 0 at t is equal to 0 and t is equal to 1. Since E, F and G are of class 1 and lambda t mu t are of class 2, therefore the functions L and M are continuous functions satisfying the condition as that gt of the lemma discussed. Hence, we can apply lemma to 11, choosing lambda, mu and g as follows. So, with this assumption lambda Vt is equal to lambda, mu t is equal to 0 and Gt is equal to L, we will get this expression. This is equal to 0, which implies that L is equal to 0 by lemma 1. Now second result indicate that on these values 0 to 1 lambda t mu t dt is equal to 0, which implies m is equal to 0 by the lemma. Hence, L is equal to 0, m is equal to 0 are the differential equation for ut and vt. Since these two equations do not involve these 2 points, so the equation L is equal to 0, m is equal to 0 are of the same for all geodesic on the surface. This establishes this fact. Now, let us write L is equal to 0 and m is equal to 0 as per this equation. In term of t, you will get f is equal to under root 2t, L is equal to del f by del u minus d by dt, del f by del u dot becomes L is equal to this, and ultimately we get the value of L as 1 by under root 2t del capital T by del u minus d by dt del capital T by del u dash, and plus 1 by 2t power 3 by 2 del d capital T by dt dot del capital T by del u dash. Since capital T is non-zero, then cancelling this term and L is equal to 0 becomes this equation. In a similar manner, we obtain for m is equal to this, and this may be treated as d by dt del t by del v dot minus del capital T by del v is equal to 1 by 2t d capital T by dt into del capital T by del v dot. This is equation number 13. Equation 12 and 13 give the differential equation of geodesic 12 and 13 are usually written as u is equal to this expression 14 and v is this expression 15, where t is equal to half e u dot square plus twice f u dot v dot plus g v dot square. This complete the proof of 2, and this proof is sufficient. Now, to prove one as the necessary and sufficient condition for alpha to be the geodesic on the surfaces, we proceed as follows. To prove the necessary of the condition, let alpha be the geodesic on the surface so that ut vt satisfy the differential equation 2. From the second expression of u and v in 14 and 15, we may write u divided by v is equal to this term, so that u del capital T by del v dot minus v del capital T by del u dot is 0, which proves that necessary of the condition. To prove the sufficiency of the condition, we need the following lemma, which is true for any curve whether it is geodesic or not. That lemma is, if u and v are as in the equation 1, then u dot capital U plus v dot capital V is equal to d capital T by dt. This is equation number 16. Now, proof of the lemma, since each of u and v have two equal expressions for it, we shall prove 16 by considering the following two cases. Case first. In this case, we prove 16 by considering the first expression for u and v. Since capital T is a homogeneous function of degree 2 in u dot and v dot, so we have by Euler's theorem this expression 17. And since t is a function of u, v, u dot, v dot, we get the expression 18. Using 17 and 18, we must prove 16. How? Substituting for u and v, we have u dot capital U plus v dot capital V is equal to this expression 19. Now we considering d by dt u dot del t by del u dot is equal to this expression, so that the expression u dot d by dt del capital T by del u dot may be expressed as expression number 21. Using 20 and 21 in 19, you may be in position to obtain u dot capital U plus v dot capital V is equal to d by dt of 2 capital T minus d capital T by dt, which is equal to d capital T by dt using 17 and 18. Now, in this we take the second expression for u and v, and we may prove that u dot u plus v dot v is equal to d capital T by dt by 17. Hence, we have this expression. This sufficiency is established by showing that a curve on the surface satisfying the condition 1 of the theorem is a geodesic. For this, it is enough if we show the condition 1 implies that u and v satisfy the geodesic equation. Let us consider u and v satisfy the condition 1. Let us assume that u dot and v dot are not 0 for the same value of t. So, del t by del u dot is equal to eu dot plus fv dot, and del t by del v dot is equal to fu dot plus gv dot implies that both are 0. simultaneously so that the condition is really satisfied. From the given condition, we may write u divided by del t by del u dash is equal to v divided by del t by del v dash is equal to theta. We may say that it means u is equal to theta del t by del u dash and v is equal to theta del t by del v dash. This is equation number 22. We shall find theta using the lemma. For the lemma, we have this expression using 22 in the above equation we get by using 17. For the above equation, we find that theta is equal to 1 by 2t d capital T by dt. Using the value of theta in 22, we will get u is equal to 1 by 2t d capital T by dt and into del capital T by del u dash. V is equal to this, which are the geodesic equation. Hence UTVT is a point on the geodesic of a surface, which proves the theorem completely. By the lemma u and v satisfy the equation u dot u plus v dot v is equal to dt by dt. Hence both the expressions satisfy the same equation, so that the two expressions for u and v are not independent. Hence these two equations are equivalent to one equation for two functions u and v, so that the curve can be defined by v is equal to fu.